Welcome back. Today we're going to talk about alternating series. So, alternating series is basically a summation where the terms of the series are alternating positive and negative. Something like, if you look at these two examples that I wrote, the first one is 1 over 1 minus 1 over 2. By replacing n equal to 1, 2, and 3, you'll get plus 3 over 4 minus, sorry, 1 over 3, not 3 over 4, 1 over 3 minus 1 over 4, and so on. So what you notice is the terms of the series are basically positive and negative alternating. And if you look at the second summation, by replacing n equal to 1, starting with 1, you will get negative 1 half plus 2 thirds minus 3 fourths and plus 4 fifths. I'm just replacing different n's and add them up. And again, what you notice is the sign are alternating, positive, negative, positive. That's why the name of alternating series shows up for this section. And generally speaking, if you're dealing with alternating series, that means there is a negative 1 to some power. So like negative 1 to the power n or to the power n minus 1 and plus 1. That power, if it becomes even, then you have a positive term. If it becomes odd, then you have a negative term. This plus or minus are coming from that. So the question in this section becomes, are these sequences convergent or divergent? Because if you remember, if it was all these terms were plus, if this was plus, plus, plus 1/3, plus 1/4, then that would have been a divergent series. By P-series test, if you remember, that would have been a divergent series. So the question is, what if we have an alternating one? Is it going to be divergent or convergent? And we'll try to answer those questions in this section. So let's focus on the alternating series test first. This is the main test that we do for this type of series. So if we have an alternating series that is like B1 minus B2 plus B3 minus B4, where Bn's are basically the positive terms, not ignoring the negative 1 to the power n. So this, if you ignore the negative 1 to the power n, the Bn is basically that the positive part of that sequence. And assuming that the Bn's are decreasing, so let's say Bn plus 1 is less than or equal to Bn, and if the limit of Bn's are approaching 0, then the series would be convergent. This is basically the test. So the test is, do you have a decreasing sequence where the limit of the sequence approaches to 0? In that case, then yes, the series would be convergent. And the idea, I don't want to give you a general proof, but the sketch of the proof is, let's assume we have B1 here. If we add B2 to it, or subtract B2, because if you remember, here is B1 minus B2 plus B3. So I'm going to put maybe B1 here. This is the idea. And if we subtract B2, so if we subtract B2, we'll end up to this point. So this gap is the size of B2. We're subtracting B2 from it, we'll end up at this point. I'm going to change the color. This is where we end up at after B1 minus B2. This is where we have B1 minus B2. Now, if we add B3, what happens? If we add B3, since we know that this is a decreasing sequence, and B3 is less than B2, I think this is a strict quality. So if B3 is less than B2, what happens is you'll end up adding a number smaller than this gap. So you'll end up somewhere here. This is by adding B3. Then if we subtract B4, B4 is less than B3. So by doing that, we'll end up somewhere here. And assume this is number line. You start somewhere on B1 and you continue moving back and forth by doing this summation. And how do we know that this moving back and forth will end? Because this is what you do. Since the limit of Bn is approaching 0, that means this gap becomes smaller and smaller. At the end, you'll end up at some point on the number line. If you add up all those numbers and subtract the other ones, you'll end up somewhere here. And this is basically the sum of those negative 1 to the power n minus 1 bi. This is where you will end up. So these two assumption is basically just to create the motion that you will end up somewhere between b1 and b1 minus b2. Okay, it's not the total proof, it's just a sketch to give you an idea why it's necessary to have these two conditions to have convergence here. Okay, so now let's look at this example. This is the very first example that I wrote, and if you remember, this is 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4. Ask yourself, what is Bn first? Bn would be, ignoring the negative 1 to the power n, Bn would be 1 over n. So now, is Bn decreasing? Is Bn plus 1, which is 1 over n plus 1? Is it less than 1 over n, which is Bn? This is the question. And simply, since the denominator is increasing, this is a true statement. So Bn is a decreasing. So it satisfies the first condition of this alternating test. And the second condition is to calculate the limit. What is the limit of Bn as n approaches to infinity? The limit of Bn, which is 1 over n, as n approaches to infinity, simply becomes 0. Because n would be infinity, 1 divided by n infinite would be 0. And now this is satisfying the second condition of the alternating test. So what can I say? Now I can say, therefore, the summation of negative 1 to the power n minus 1, Bn, which in this case is 1 over n, is convergent. Okay, it is important to check both of these conditions. If one is true and the other one is not true, if this wasn't 0, then you couldn't say it is convergent. In that case, it would be divergent. Okay, so if you don't satisfy the first condition, then the series would be divergent. If you don't satisfy the second condition, the series would be divergent. Okay, it is quite important that you check for these cases. Okay, so here, by the way, I think I wrote here for all n. Just for all n, I think you can maybe avoid the first maybe 2-3 terms. After that, if it's true after a certain point, then you can still use this alternating test. I think the textbook uses for all n, that's why I stick with it. But generally speaking, if you know this series is convergent, for example, then if I add a 5 at the beginning, if I write 0 plus this, it's an increasing first, then it becomes decreasing. It doesn't really make that much difference, right? So adding 1 or 2 term at the beginning doesn't matter, doesn't really affect the convergence or divergence. But if it's infinite number of them, then that would be quite an issue. Here's another example. How about this one? Is it convergent or divergent? By the way, the question in all these is this series convergent or divergent? We don't know what is the end of this. What would be the summation here? We don't really care at this point. That would be an issue for later on, but at the moment we only want to figure out if it's convergent or divergent. I wrote equalities just to see what are the first couple of terms. So if you're looking for convergence or divergence of the series, try to write down a couple of terms just to see how the behavior of the series looks like. So if I let n equal to 1, you'll get negative 3 divided by 3, I'm replacing n, plus, if you replace n with 2, you'll get 6 divided by 7. If you replace 3, you'll get, what do we get? If you replace n equal to 3, you get 9 divided by 11 or something. Okay, so now ask yourself, you can very easily see that the series is kind of decreasing in terms of positive terms. What do I mean by that is, first figure out what is Bn. Bn is 3n divided by 4n minus 1. Ignore this negative 1 to the power n. That's the bn. Then if you ask yourself, is bn decreasing or increasing? Is decreasing or not? You can check that. How do we check it? You can take the derivative and figure out if it's decreasing or not. So here I'm going to do that. Let's try. So the derivative would be 3n divided by 4n minus 1 derivative. Denominator 4n minus 1 squared. Numerator would be 3 times 4n minus 1 minus 4 times 3n. And if we simplify it, denominator is 4n minus 1 squared. I don't need the parentheses. And if I distribute 3 times 4n and minus 4 times 3n will cancel out, so you'll end up with a negative 3 in the numerator. So what you know is that the derivative is always negative because the denominator is always squared. So this is always negative. That means it is a decreasing sequence. You can check it through the numbers at the beginning just to give you an idea. But now if we calculate the limit n approaching to infinity of bn, what we get is limit 3n over 4n minus 1 as n approaches to infinity. And as n approaches to infinity, you can divide everything by an n. I think you should know that by now, and you'll end up with 3/4 the limit. So now we satisfy the first condition that the bn is decreasing. We satisfy this, but we didn't satisfy the fact that the limit must be 0. Because now for the limit, we got the limit is 3/4. So this condition is not satisfied. If one of the conditions is not satisfied, then you can say the summation of negative 1 to the power n bn is divergent. Because it means that at some point, what do you have? This tells you that at some point, what you have is kind of alternating. You end up with a number, then you go to the next one, you come back to this. This gap doesn't really decrease that much. Because as you go infinite, this length, the difference between bn and bn minus 1, kind of stays a fixed value. So the gap would be stable. Every time you add a number, the same you subtract that number. Okay. So you kind of add 3/4 at every step and subtract 3/4. That basically tells you that. So in this case, if you satisfy both conditions, you have a convergence series. If you don't satisfy that, you have a divergence series. So maybe at the end here I should say otherwise diverge. Okay, so it's quite a strong test for the alternating. Okay, here another example. Negative 1 to the power n plus 1. So first figure out, you don't need, if it's too complicated to figure out what is n equal to 1 and 2, don't do it. But for me, suggestion wise, I always try to write a couple of terms to see how it looks like. If I pick n equal to 1, I get 1/2. If I pick n equal to 2, I'll get 4 over 8, 9. Then I'll make my assumption based on that. Is the series decreasing or increasing? I'll kind of look at that, and you see that this is 4 over 8, then it'll go to 4 over 9. So I'm claiming that probably this is a decreasing sequence. So first bn is n squared divided by n cubed plus 1. Then is the series increasing or decreasing? I'll calculate the derivative, bn derivative. By the way, this notation is not correct. You have to, maybe it's better to write in terms of x, then take the derivative, but you can assume that the n is continuous and I'm taking the derivative. N squared divided by n cubed plus 1 derivative. If you're taking the derivative, your assumption is that the function that you're taking the derivative from belongs to a space of continuous functions. But here, when we say n normally is discontinuous, so I should write x here, x cubed and x squared. But I'm gonna stick with the same variable, and change my assumption and say we're dealing with a continuous set of numbers, not discrete. It doesn't really affect anything. It just makes it mathematically more correct. So the derivative denominator doesn't really make any difference because it's always positive. Then the derivative would be 2n, 3n, sorry, n cubed plus 1 minus, here you have n squared times 3n squared. And if we simplify, what we end up with is something squared in the denominator, and the numerator would be 2n to the fourth minus 3n to the fourth. That would be negative n to the fourth plus 2n. Okay, and you can factor out an n just to make it more clear for yourself. You can factor out an n, and you have n cubed, negative n cubed plus 2, and divide by n cubed plus squared. So as n increases, this becomes a negative always. Negative times a positive, it's always negative. So this is a decreasing. So if we have a decreasing function, we satisfy the first condition. So if we satisfy the first condition, I'll check for the second one. Is the limit of the bn, the limit n squared divided by n cubed plus 1 as n approaches to infinity, is that limit 0 or not? So this is the second case, and if we calculate and divide everything by n squared, maybe that would be better. Just to remind you of how you calculate this limit as n approaches to infinity. You can use Hopital rule as well, that's totally fine. And this becomes 1 divided by infinity, because this simplifies to simply n, and here this one would be 0. So you have 1 divided by infinity, which basically gives you 0. So it means that we satisfy the second condition as well. So now I can say the summation of negative 1 to the power n bn is convergent. Again, we don't know what the limit is, we just know that it's going to end up converging to a certain number. Okay, so this is quite important to deal with this. And by the way, if the series is not decreasing, if it is increasing, it's already easy to say this is a divergent series. So if you know that the numbers are increasing, something like from here to there, then the next one is larger, and the gap between these numbers become larger, and then in that case, bn would never be convergent to 0. Okay, so normally what you have is the fact that the bn's are decreasing. You have this fact. The only thing that you need to check is that the limit is approaching 0. If it's not decreasing, then you don't need to really check the limit, because that's quite obvious that that limit wouldn't be 0. Okay, so one of the consequences of this is dealing with alternating series estimate. So how do we create an estimation of where we're going to end up if we're dealing with a convergent series? So assume that we have a convergent series for alternating form, meaning that the bn's are decreasing, also the limit of bn's are approaching 0. So if we have these two, then what can we say about the limit? It turns out that if you start with b1 and subtract b2, you'll end up here, as I said. This is b1 minus b2. Then if we add b3, you'll end up somewhere here. But what we know is that these numbers are just going back and forth, and you'll end up at some point finally, this would be the limit, the s, the total summation. But the difference between this summation and if you cut it off at this point, for example, if you cut it off and calculate the distance between these two, this is the error. s minus sn. Then what is that? It's smaller than the amount that you're gonna add for the next step. This is always less than bn plus 1. Because bn plus 1 would be always, in terms of length, it would be larger than the gap that is gonna go back and forth. Okay, and that gap basically becomes, at most, it becomes the difference. So the Sn minus Sn, the S minus Sn is basically the summation minus the sum of the first nth term. That is always less than, in terms of absolute value, it's always less than the next term of the sequence. Okay, this is just, again, I didn't prove it, I just gave you a structure of how the proof looks like. I didn't want to spend time on that. And so we can use this kind of to give a good estimation of where our convergence approaches to, or you can say, okay, what is the remainder or the difference of the S minus Sn less than 2? It gives us a good estimation. So here, for example, we approximate the sum of the series up to 3 decimal places. If we want to do that, what we can do is you can use this idea and say, okay, if I want to create up to 3 decimal places, what do I want is I want the summation, the total summation, minus the sum of the first nth term. I want that to be less than 3 decimal places, meaning it would be accurate up to 3 decimal. So I want that to be less than 0.001. Okay, so if I want the summation to be accurate up to that digit, the question becomes, what should I pick for n? What is n? Then after I find n, then I will add up the first nth term of the sequence. Okay, and from this theorem, you kind of learn that this difference, the remainder, is less than bn plus 1. So it's enough for me to say, okay, let's figure out where bn plus 1 is less than or equal to 0.001. Then I can find out what is n. So what I can say is, where do I get, by the way, bn is 1 divided by n times 4 to the power n. So the question is, where do I get bn or bn plus 1? Where do I get this term? 1 divided by n 4 to the power n be less than 0.001. It's normally supposed to be bn plus 1. So let me write this. You can write bn plus 1, which is 1 divided by n plus 1, 4 to the power n plus 1, less than 0.001. Or you can replace with bn and just say, okay, I'm gonna cut it off at bn plus 1, not at bn. It's either way the same. Okay, so here, how do we solve this inequality? You can simply replace different numbers to see what happens. For example, if I pick n equals to 2, to see if it's still less than that, if this inequality is satisfied or not, what do I pick is, let n equal to 2, what do we get is 1 divided by 3 times 4 to the power 3. What is that number? I should have a calculator at the moment. So this is, sorry, 1 second, let me get a calculator. Just to give you a good accurate data. 1 divided by it is 0.0052. You can check my work to see if it is correct or not. So if I will let n equal to 3 because I want this number to be less than 0.001. So I can pick a different one. Next number, n equals to 3. What do I get is 1 divided by 4 times 4 to the power 4. And that simply is 1 divided by 1 divided by 4. Okay, so now what do I get is 0.00097, so on. So now I know that if I cut off the sequence at n equal to 3, that would be an accurate assumption because bn plus 1 is less than 0.001. That means the difference between the exact value and our estimation is less than 0.001. So this n equal to 3 is basically, what do I need? It means add up s is almost the same as s of 3 with the difference of at most 0.001. So I just need to add up the first 3 terms. I can say, okay, let's add up sum n from 1 to 3, negative 1 to the power n, 1 divided by n times 4 to the power. And this is basically replacing n with 1, 2, and 3, which is negative 1 divided by 4, if I'm not mistaken. Just make sure that you double check my work so I don't make any mistakes. 1 divided by n equals to 2 would be 2, 4 to the power 2, and minus 1 divided by 3, 4 to the power. We already have negative 1 over 4 would be negative 0.25 plus 1 divided by, let me do this one too, 1 divided by 2 divided by 4 to the power 2. It is 0.03125. And then if I divide by 3, I got this number already, 0.0052. So if I add up all these numbers, that would be a close approximation for our result. I have 2. Sorry, I'm using calculator, that's why I'm quiet. Here we go. I got minus 0.22395, almost. Okay, so this is our estimation of S. It's not accurate, but it's approximately S is close to this number with a difference of at most 0.001. Okay, so you can quite use this to say our error, the remainder, is less than bn plus 1, by the way. This is what we said. And in this case, bn plus 1 is 0.00097, which is definitely less than 0.001. Okay, so this is quite the idea of using this alternating series estimate. Again, I didn't prove any of this. The proofs are available in the textbook, but if you kind of need to see the proof, always the idea is that if you add up the first couple of terms, let's say this is, you start from b1 and you add b2 to it, you'll end up here. Then you subtract b3, you'll end up here. Then you add b4, you'll end up here. What happens is this is b2, b1 plus b2. Let's assume this is negative. And then you'll have minus b1 plus b2 minus b3 or something like this. This would be b1 plus b2 minus b3 plus b4. Okay, so you're adding and subtracting numbers. At the end of this, you'll always end up in somewhere in the middle, and you kind of approach to that number. It's not going to be exactly halfway. It's just going to be the idea that you're going alternating back and forth. So you'll end up somewhere in the middle. And the difference between this number and whatever you cut it off, let's say I cut it off at this point, at b4. This difference, this is s minus, this length is s minus S of 3 or 4, in this case 4. This difference is less than what you do for the next one. This is B5, this length. That length is B5. And you notice that is less than B5. Okay, this is basically that approximation. And we say our remainder will always be less than that. Okay, this is a kind of how you use this approximation. Okay, I think it's quite easy, this section. Next time we talk about absolute convergence and ratio and root test. Still dealing with alternating. So I'm going to stop at this point.